Hello, my name is Meredith Wilcox, and my topic is health effects on the depletion of the ozone layer. Okay, I'm going to start with some background information. I'm going to discuss what ozone is. Ozone is a molecule containing 3 oxygen atoms. Ozone is found in both the lower atmosphere and the mid-atmosphere. The lower atmosphere is called the troposphere, and that contains a little less than 10% of all the ozone on Earth. That ozone is considered bad ozone. It consists mostly of smog, therefore it's considered a pollutant. It's harmful to breathe and damaging to vegetation. The rest of the ozone, a little over 90%, is located in the mid-atmosphere, and that's called the stratosphere. That ozone is considered good. What it does is it absorbs a lot of the solar radiation from the sun, so it prevents that radiation from reaching us down at the surface. And that 90% of ozone in the stratosphere, that's what we know as the ozone layer. Just to give you an idea of how many ozone molecules there are, for every 10 million air molecules, there are 2 million oxygen molecules and only 3 ozone molecules. Okay, slide number 3 just shows a picture, a diagram of the atmosphere, shows you the troposphere and the stratosphere, and it shows you where within the stratosphere the ozone layer is located. It's approximately, in the middle of the stratosphere, maybe a little bit lower. The benefits of the ozone layer, I actually just mentioned it. Ozone molecules absorb harmful ultraviolet radiation, most importantly ultraviolet light. The ozone layer absorbs 97 and 99% of ultraviolet light. Okay, now I'm going to discuss the creation and destruction of the ozone. This occurs both naturally and by man-made chemicals. I do include in the PowerPoint a number of chemical equations showing the destruction and creation. I'm just going to give you a general idea of what happens. Ozone can be created when an oxygen molecule absorbs ultraviolet light that separates the 2 oxygen atoms. One of those oxygen atoms can then react with an oxygen molecule to form an ozone molecule, an O3 molecule. Ultraviolet light can also destroy an ozone molecule. When an ozone molecule absorbs ultraviolet light, it can separate into an oxygen molecule and an oxygen atom. A single oxygen atom can also react with an ozone molecule to destroy it. Okay, so if we're talking about how CFCs destroy ozone molecules, what happens is when CFCs reach the stratosphere, they can absorb ultraviolet light, and what results is a single chlorine atom. That chlorine atom can then react with an ozone molecule, which is highly reactive, and break apart that ozone molecule. A few chemical reactions down the line, that chlorine atom is re-released into the atmosphere, and it has the potential of starting the whole ozone depletion cycle once again. So one chlorine atom can continually break down ozone molecules. Okay, a quick history on the depletion of the ozone layer. This idea was first introduced June 28, 1974 by 2 chemists from the University of California, Rowland and Molina. They recognized the involvement of CFCs in the depletion of ozone and called for the ban on CFCs. There was a lot of opposition to the theory, mainly from industry spokespeople and politicians, the main reason being that the CFC industry employed a lot of people and made a lot of money at the time. In 1985, there was the discovery of the Arctic ozone hole, and by 1987 the Antarctic ozone hole had lost 50% of its ozone. This eventually led to the Montreal Protocol in 1987 calling for phase-out of all ozone-depleting substances, including CFCs. It was an international agreement, it especially targeted those ozone-depleting substances which contributed most to the global atmospheric chlorine input. It also named CFCs as the replacement of FCs. Sorry, HFCs were the replacement of CFCs. Okay, now CFCs were genetically were engineered without the propensity to chemically break apart ozone molecules. They replaced CFCs in air conditioners, refrigerators, insulating foam, and automobiles. It's actually recently been discovered that the strong bonds of HFCs act as a heat sponge in the atmosphere, absorbing energy from the sun that would otherwise be reflected back into space. So in a sense, HFCs contribute to global warming. And that is one of the consequences, not so much of the Montreal Protocol, but the decision to use HCFs as a substitute for CFCs. The Montreal Protocol did lower the level of quote-unquote ozone depleting substances in the atmosphere. So it successfully tackled the issue of ozone depletion, but then created a new problem with the HCFs and global warming. Now we're going to talk about health effects that result from UV exposure. As the ozone depletes, more UV radiation can reach us, and thus can increase the risk of these health effects that I'm about to discuss. As far as the eye, there's multiple conditions tied in with UV exposure. I'm going to concentrate on cataracts. Cataracts result from the accumulation of oxidized proteins in the lens of the eye, and it leads to gradual loss and transparency of the lens, and often results in blindness. Blindness can only be avoided if the lens is surgically removed. The economic and social impacts of cataracts within the public health field is enormous. Cataracts are the leading cause of blindness in the United States, and the public health care costs of cataract surgery in 1992 exceeded $3 billion. As far as the immune system, UV exposures can lead to a decrease / delay in the body's immune response. This can occur locally within the ultraviolet exposed skin, but it can also occur at distant sites depending on the UV dose. Immunosuppression becomes problematic when dealing with infectious diseases, since the body depends on an active immune system to fight off such diseases. Okay, as far as health effects on the skin, we have sunburns, which everyone knows about. Photoaging, that's when cells in your skin are damaged, and symptoms include wrinkles and loss of elasticity. There's also skin cancer. It's widely known that ultraviolet radiation exposure increases your risk of skin cancer. Scientists and researchers disagree on exactly how it increases your risk. Some believe that your total overall UV exposure is what needs to be looked at. Others believe that your risk plateaus at a certain point, so you need to look at the amount of childhood exposure, and others don't even believe it's your total exposure, but the intensity, so the number of sunburns that you acquire. Conclusions and recommendations. It is known that the Montreal Protocol has successfully tackled the issue of ozone depletion, but it has created problems with HCFs and global warming. So I believe a suitable replacement for HCFs must be found, one that deals with the issue of ozone depletion without increasing the burden of global warming. Although the slowing of ozone depletion means that the ozone layer will be able to protect life on Earth from harmful solar radiation, I believe that individuals must do what they can to prevent ultraviolet-related health effects. There are different determinants that lead to ultraviolet-related health effects, such as genetics, so your pigmentation, also sun-seeking behavior, how often you go in the sun, how long do you use sunscreen, and age. So even though we can preserve the ozone layer and it will be there to protect us, we still need to do what we can as individuals to decrease our risk of these UV-related conditions. Okay, and that's my presentation. Thank you.